Okay, thanks. Hello everyone, I'm Suhas Pai, NLP stream owner at AISC, and I welcome you all to another spotlight session. We are having a bit of a mini series on NLP interpretability this week. So we were glad to have Yuval Pinter from Georgia Tech in yesterday's session, who spoke about interpretability and explainability in NLP, and also on his famous paper, Attention is Not Explanation. In case you missed it, you can find the video on our YouTube channel. But now let's come to today's talk. Well, if 2018 was the year of BERT, then 2019 was the year of BERTology. We had several interesting papers that tried to demystify the inner workings of the golden goose that is BERT. One of the most valiant efforts in that endeavor comes from the authors of the paper Visualizing and Measuring the Geometry of BERT, accepted at NeurIPS 2019, who showed several fascinating insights into how BERT representations encode syntax as well as semantics. We are delighted to have the authors of this paper from Google Research speak at our spotlight session today, Andy Coenen, Anne Yuan, and Emily Reif. Over to our guests now, who will introduce themselves and continue with the presentation. Thank you.
Hey everyone, I'm Anne, and these are co-authors Andy Coenen and Emily Reif. The title of our paper was Visualizing and Measuring the Geometry of BERT. And just to give a quick introduction into what is BERT. So BERT is a general purpose language model that came out in 2018 that generates embeddings for text that turn out to be very useful for a variety of downstream tasks, including question answering, sentiment analysis, and entailment classification. This figure on the slide is from the BERT paper, and it shows that on a set of language understanding tasks, BERT was able to attain state-of-the-art results. Since then, BERT has been surpassed by several other models, but by and large, those models use BERT as an underlying architecture. So BERT was trained on two tasks. One is fill-in-the-blank word prediction. So BERT was fed sentences where some of the tokens were masked out, and BERT was asked to predict what the correct token was. The second task was to predict whether one sentence followed another. The architecture of BERT comes down to these transformer blocks. And actually BERT is an acronym that stands for bidirectional encoded representations from transformers. So how do we get from words to embeddings? So given an input sentence like I went to the store, the first step is tokenization. The next step is to feed the tokens into an encoder. That encoder generates embeddings for each of the tokens, and this process repeats itself either 12 times for BERT base or 24 times for BERT large. To go into a little bit more detail about the transformer, the central idea is that each of the tokens within a sentence is able to spread its attention across the other tokens in the sentence to basically spread the influence of the other sentences in generating its own embedding. And Andy will dive into transformers a lot more in his section on syntax.
Yeah, so we started this project last year, kind of getting together and asking one big question, and that's, does BERT have some notion of syntax? We started that very generally and sort of whittled our way towards some of the results that we wound up publishing. But it was very motivated by this question, like, it's clearly doing well at all these language related tasks, like state-of-the-art on all of these things, and how is it doing it? Is it reasonable to expect that it is knowing something about the actual syntactic structure of sentences? And if so, like, how is that information encoded? What's mediating it? And can we sort of tease it out of BERT's internal workings? So we started this approach, or we started attacking this by looking into attention. So this section is all about attention probes and dependency relations, and I'll get into a lot more detail on that. But we really wanted to leverage attention and sort of like look into attention as maybe the spot or the feature of the language model that was really mediating this this sort of syntactic representation, or at least an approximation of it. So just for a little bit more context and go back into some BERT background, how does BERT encode information involving a word or token's meaning into that embedding? So the big leap for BERT in these transformer models is that they inject the context of words around it, or information about the context of the words into that embedding. And it does this by sort of passing the information contained in other tokens into a given token as it passes down through the layers. And it specifically does that trick by interword attention. So as the words pass through, as the word embeddings pass through the layers, their meaning gets built up by attending to other tokens or other words in the sentence. So we can see here like a little visualization of what that attention kind of looks like. So for this sentence, the old fox saw the new dog. This is just a matrix of the attention being paid to the other tokens with special CLS and SEP tokens at the beginning and the end of the sentence. So that picture before was one specific attention head. So it turns out the network has, in BERT Base's case, 12 different layers, each with 12 attention heads that are mediating attention being paid from one token to the other. So as the word gets passed through, or as these embeddings get passed through the layers, these varying amounts of attention are sort of shuttling information from one embedding into the other embedding. And you can sort of see these interesting patterns emerge of, words paying attention to the next token, or words paying attention to the previous token, or to the CLS token, which is kind of neat in and of itself. So it's natural to think, this attention mechanism is clearly shuffling information about the context of embeddings into other embeddings. And is it reasonable to expect that this is kind of encoding grammar? Like the grammar of a sentence is essentially the relationship of all the words to each other in a structured way. Does this attention mechanism encode grammar? Does it sort of inject grammar as information into these embeddings? So we wanted to sort of figure out a way to attack this problem. So recall from my earlier slide, each token pair has an attention that mediates sort of the information transfer between those embeddings at each layer and each attention head at each layer. So you can sort of see for the word pair, the fox and the dog, you have different attentions being paid between those two tokens. And that sort of represents the amount of one embedding's context being injected into the other. And it's natural, like I said, to ask the question, does this encode their grammatical relationship? Like these two words do have a grammatical relationship, and is it correlated to the attention being paid? So for a single attention head, we can get one value. And if we take this for all 144 attention heads, we can concatenate those attentions into a 144-dimensional attention vector. So basically, we're taking, for a given word pair, all of the different attention values across the entire network and looking at it as sort of an attention embedding, an attention vector representing how much attention is being paid at all of the different points in the network. So do these attentions contain information that corresponds to grammar? So we're specifically going to look at the dependency parse tree. This is a specific way of parsing sentences. There's a number of different ways. This is one that is widely used in the linguistics community. And basically, it encodes sentences as trees with edges defined by specific types of relationships called dependency relationships. And in this parse structure, each inter-word relationship is like classified in a different way. So you can see a simple one would be something like the dog is bridged by a relationship called the determiner. And for any of these sentences, we can sort of find their dependency parse tree and then see if those dependency relations correspond to the given attention vectors. And what we did to check this is just train a simple linear classifier to basically ask two questions. The first was, are any two token relations, are any two tokens connected via a dependency relation based on the attention vector? And we found that for that binary prediction, we could answer with 85% accuracy. And then more interestingly, could we predict which specific dependency relation? There's like 27 different dependency relations in the standard grammar. And we found that we could predict with 71% accuracy what specific dependency relation it was based on the attention vector for those two tokens in the network. And this figure just sort of shows an overview of those results for all the different dependency relations. I'm not going to get into too much detail here. So that's really, really interesting. Like that's some sort of fascinating evidence that there is some syntactic information contained in BERT and that it's being mediated by these attention mechanisms. So we sort of followed it up by thinking a little bit about what that information looks like in the embeddings. So attention is clearly injecting some sort of syntactic or parse tree information into these embeddings. And we wanted to know, is there a geometry that we can tease out? Is there some representation that's easy to understand in these embeddings? So going back to the fundamental question, does BERT encode syntax? Well, we know that it does really well on syntax-dependent tasks. But is it reasonable to expect that that information is contained in the actual embeddings that these tasks are using? So we followed up on a paper from 2019, another BERTology related paper, and this is Hewitt and Manning from Stanford's paper, A Structural Probe for Finding Syntax in Word Representations. So I'll go into a little bit more detail about this in a few different slides, but what they did is they trained a probe that basically is a matrix that transforms the BERT embedding space into a different subspace, like a projected space, in which the squared L2 distance in that space between tokens, that distance squared, is the same, or in codes, it's similar to the distance between the words in a parse tree. So it's a lot to digest, and I'll go into a little bit more detail in a sec. But basically what they could do with that probe was take all of their BERT token embeddings, apply that probe, get a distance matrix between all the different projected embeddings, and then from that distance matrix, they could fairly accurately reconstruct the dependency parse tree. So you can see in this little figure, this is right from their paper, I think the top tree is the real tree, and the bottom is their sort of projected observed tree. So they could take those words, project them down using this really simple linear transformation and find the almost exact dependency parse tree, which is really, really neat. So we sort of followed up on this and looked into it a little bit. And it turns out that there's some really interesting things about these parse tree embeddings. So they're almost perfect. So what this is and what this means is something I'll follow up in a little bit, but this figure sort of illustrates what I mean. On the left, all of these are PCA projections of parts of trees in high dimensional space. So on the left, you have the actual BERT embedding projected into this Hewitt and Manning subspace, using this syntax tree probe. You project these tokens into some sort of tree space. And if you flatten it out with PCA, what you get is something that looks very strikingly similar to B, which is the perfect tree being projected down. So basically, if you have a tree in high dimensional space where every single edge is orthogonal to each other, and you project that down using PCA, that's what you get with B. And you can see that the BERT embedding looks very similar to that, which means that this syntax tree is being represented in embedding space very, very faithfully, very, very accurately. And you can see that in the random case, it's just a smear. It's just kind of random when you project it down in contrast to these nice trees. So to clarify some of this tree stuff, because it is a little confusing and a little complicated, what we mean by the perfect tree is that for a given tree distance, like in a sentence, a parse tree, the edge distance from a node to another, in this case, A to X, X to B, each being a distance of 1, that tree distance would be 2. So like in a sentence, any two dependency relation edges you count as 1, and you can kind of count the distance between tokens in that parse tree. If you projected that tree geometrically into like an embedding space, what you see is that that distance is just the square root, right? So from A to B, you have A to X, X to B, it forms a right triangle, so the hypotenuse would be the distance of square root of 2. And this is that neat property that Yuan and Manning found, was that projection into the sort of syntax tree subspace, the squared L2 distance, meaning this square root of 2 edge, that squared is the same as the distance in the parse tree, which would be 2. And they didn't really, they put this in as a footnote. They were like, we don't quite understand why it's this weird squared relationship. But it turns out it's this really nice property. Like if the tree is being represented in a high dimensional space, you sort of automatically get that feature because these two edges wind up being orthogonal to each other. So you get this nice right triangle and you get this squared L2 distance relation, which is really, really cool. And it sort of means that BERT can, in fact, pack these trees into the embedding space in a really nice tree-like way, which is neat. So we kind of looked into this a little bit more, and we have a ton of these examples in the paper and a follow-up blog post where you take a dependency parse tree and you compare it to the BERT sort of representation. So this is just a PCA plot, again, of the BERT embeddings projected into the tree space subspace by this Hewitt and Manning type probe. And you can see it like really nicely splays out the tree in almost the exact sort of shape as a parse tree. But there's some other really, really neat features. So one thing that we observed fairly consistently was that certain words are much closer to each other than you would expect based on their tree distance. So in this example, sale of and part of these two tokens represented by the dashed red line connecting them indicate that they're a lot closer to each other than you would expect just based on their tree distance. So like part of and sale of are pretty far away in the actual tree, or the dependency parse tree, but very, very close in this sort of syntactic subspace. And it's neat that these specific tokens wind up being close. Like it turns out that intuitively, it feels like they might actually ought to be close. Like sale of and part of are kind of phrases that feel very similar, or sorry, they occur very commonly together. They feel like they might actually, it's kind of reasonable intuitively for them to be close to each other. Same thing over here where same as winds up being close to each other in the BERT representation, even though it's a little bit further away in the strict dependency rule parsing. So we followed up on that a little bit more, and it turns out that these different dependency relations have sort of widely varying distances depending on their specific identity. So certain things like compound participle wind up being very, very close. And here's like an example of what that is. So they shut down. And again, it's like this common bigram. It's like these words sort of work together in a way that makes them very, very sort of similar, like working as a unit almost. And contrast that to a edge that's very, very wide and distant. So specifically a parataxis, which literally is just a joining of two unrelated phrases. That's like what it means in Greek. So it's interesting. There's like this spread of distances where BERT is clearly learning that some things are more related or sort of more closely aligned than others, even though they're sort of just all the same in the standard dependency parse tree. Cool. And we can show some of these later.
Cool. So go ahead.
maybe, okay. So did you find any evidence about BERT encoding the depth of a word in the parse tree?
Yeah, so Hewitt and Manning, they've trained two different probes.
Mhm.
So the first was to train it for the distance between nodes in a parse tree. And the second was to train a probe to find the depth in a parse tree. So we focus most of our work on the distance because we were kind of just looking at parse tree stuff, but the Hewitt and Manning paper it's 50-50. They sort of do both of those tasks.
Okay. Can you please go to the slide about the structural probe, and maybe could you please expand a little on the structural probe and yeah, what is the linear transformation? I think you had one at the back.
Maybe this slide.
Yeah.
Yeah. So basically, the way that it works is you have you have BERT embeddings in 768 dimensional space. What they did was they just trained a matrix transformation. The probe is a matrix that transforms that 768 dimensional space into some other subspace. So they actually did different ranks of transformation matrices. They did full rank to 768, so 768 BERT to 768 projected, but they also did like 16 dimensional projected it down into an even smaller subspace. And the task was basically find this probe to translate into a subspace in which the edges, the distances between the tokens were analogous to their parse tree distances. And it's kind of neat. They found that actually worked when you shrunk it down to something as small as 16 dimensions. And I think it's really interesting that it's really interesting because what they illustrated was that it turns out that it's sort of important for these edges to be orthogonal. So if all the edges between the tokens are orthogonal, you get that nice little square root distance thing. But also you can just pack more edges in. So 16 dimensions is a lot of dimensions to fit most sentences that are 10 or 20 or whatever words long. You can kind of still get that effect. Does that make sense?
Yeah. Thanks for answering. I think so. You primarily worked on dependency parse trees. I was wondering if there has been other work on looking at other types of parse trees and how what represent, for example, like constituency parse tree. Are you aware? Yeah.
We actually are just starting some work doing constituency parse tree reconstruction too, and we're going to try the same trick. There's some reasons why the math is a little easier with dependency parse trees. So that was the natural first step, but we're gonna get back into it and try it with constituency trees as well.
Mm-hmm. We have a question from the audience. Okay, so the question is, it's a quite straightforward fact that if each edge lives in its own subdimension, then the path distance is L1 distance. It's also squared L2 distance if all edges have equal weights. Why deal with L2 at all?
Sorry, why did they do L2 at all?
Yeah, I think the question is, let me try to parse it. Why L2 and not L1 is the question. Basically, that's what's being asked.
For our observation or for the Hewitt and Manning paper?
We'll come back to that question a little later because I'll clarify with a poster.
Okay.
But there's another question in the meanwhile. What would the orthogonality of vectors in the Hewitt-Manning paper suggest about parse trees? Things like independence between tokens?
Yeah, that's an interesting question. I don't know.
Yeah, I mean, it's interesting because this is independence between tokens. I mean, this is a specific subspace that has been entirely
trained to pick out these syntactic relationships. And so I wouldn't say it's necessarily like that the tokens are independent. And also given that they have these, that, you know, based on the distance between them, you can reconstruct this, this parse tree, that they are highly dependent. But I think the fact that they're orthogonal does start to point at the idea that the syntax, that there is some, you know, in this subspace, and therefore in BERT's original space, there are interesting directions for specific relationships like parataxis, et cetera, et cetera. And that there's some way that those relationships are transferable between sentences. So maybe in that way, the tokens are, you know, not just dependent on each other, but definitely like when a sentence is embedded, it, you know, there's a whole context of what am I trying to say? Of like grammatical relationships that are similar between different sentences, between the same grammatical relationships in many sentences, and so in that way they're sort of dependent on that as well. I don't know if that's really answering the question though.
So one interesting observation, and we didn't publish this. This is something that I just did a few weeks ago. I asked the question: for a given dependency relation, is the vector between those two embeddings, like, is the delta vector between those, like, are they oriented in the same direction? And it turns out they're not. They're like pretty much random, which is interesting.
Yeah, so maybe
I'm not totally sure how to
saying, yeah.
Yeah, exactly. It's like it's really tough to know exactly what's going on here. My hand wavy, sort of very informal, intuitive explanation is that there's just a lot of dimensions to pack a lot of data into. And BERT is kind of just scattering it in there in the way that it can maximize whatever information it needs to do its downstream training thing.
So a single grammatical relationship could be encoded separately in multiple dimensions?
Yeah,
okay.
I don't know though. We haven't like really formalized that at all, so.
Does that answer the question?
Yeah, I think so. I think we can move on to the next section.
Cool.
Thanks.
Cool. Yeah, as we've been demonstrating, BERT embeddings are shown to encode a lot of syntactic information, but we also know that BERT embeddings are really useful for tasks that involve semantic understanding. And so that led us to wonder whether maybe the picture of what's going on here is that BERT embeddings encode both semantic and syntactic information, but in separate subspaces. And so to try to tease out what that subspace would look like, we essentially replicated Hewitt and Manning's setup for training a projection probe to transform BERT embeddings into an alternative subspace, except we changed the loss function rather than optimizing for resemblance to tree distance. We optimized for distances between embeddings for words of the same sense to be closer to each other. So we tried to find a subspace where the embeddings for different senses of a word would be farther apart and embeddings for words in the same sense would be close together. And we found that after we trained this probe and we applied it to BERT embeddings, we were able to slightly improve on the state of the art for a standard word sense disambiguation task. You can see in this figure, we show accuracy with just straight up BERT embeddings and also accuracy with the probed embeddings. And so this sort of confirms our hypothesis that BERT embeddings encode many types of information, semantic and syntactic information, but in these sort of separate orthogonal subspaces. And Emily is going to talk more about that semantic subspace.
Yeah, so as has been discussed, BERT's embeddings are fundamentally different than the word-to-vec embeddings because they have this notion of context. And to just visualize this explicitly, in word-to-vec, glove, etc., you have one embedding for a given word, no matter the context of that word. And even with that, the word-to-vec paper showed in all of the follow-up work on analogies and all sorts of things, how subtle that embedding space is. But with BERT, of course, you have this whole other layer of context, as has been discussed. So the bark on the tree is red, and the dog will bark at you. These barks have totally different embeddings as they move through the network. And yeah, so as Anne was discussing, we first wanted to see, well, okay, how well can BERT just automatically, or given labeled corpus of different word senses, how well does it do on that labeled corpus? And we found that yes, as Anne said, it does indeed know that bark is different than bark. Tree bark is different than dog bark. But there's more to the story there, right? Because those are only two specific senses, and we as humans understand much more subtle contexts of a single word in different sentences. And so we wanted to, more qualitatively assess this. So we created this visualization, basically for a given word, find 1,000 instances of that word in different sentences, get the embeddings of those words, and project them into 2 dimensions using UMAP. And we did find overall, I'll show you all in a second, but the different senses of the word typically are spatially separated, and there is more further structure relating to finer shades of meaning and tense and all sorts of things. And just as a quick aside, why did we use UMAP? So basically we have these 768 dimensional embeddings. We need to project them down into 2 dimensions. PCA is one clear option, but that tends to lose some of the subtleties. TSNE is another good option. UMAP is similar to TSNE in a lot of ways, but it was recently released by McInnes, is that how you pronounce his last name? And it just has some speed ups and is better at preserving the data's global structure. You can also add new data points after the initial projection. And for more information, Andy wrote a great blog post about UMAP that he might talk about later if we have time. And so now I'm going to show you all these demos. Right, so we can hide this. So these are all of this is the word walk projected into 1,000 sentences, as I said, and then these are the last layer embeddings. And these labels are for a given cluster of sentences. Every point represents a sentence. And for this cluster of sentences, what is a main word that pops out frequently in this cluster? So immediately we see these this top cluster is a 3-minute walk, a short walk away, short walks, but where walk is the noun. And similarly down here, you got the sky walk, you have your contemplative walk, the walk begins. So you have these nouns, and then down here we have the verb cluster. And in fact, if we visualize this by part of speech, we color them by part of speech, that those clusters absolutely pop out as well. So not only so it's definitely clustered by part of speech, but also finer shades within there. And then if you're curious what this little cluster is, this is like the baseball walk. Both used as a verb and as a noun, but either way, it's like a totally separate thing, probably just because of the context of all the fact that it's baseball related, and probably there's so much baseball vocab that BERT thinks of it as substantially different.
Can you zoom in just a little closer too?
Absolutely,
I just want to see if the top all verbs? Oh yeah.
Yeah, the top is all the baseball verb walk, I'm not going to try to talk about baseball, but the verb versus the noun. So another one, die. Of course, with the part of speech, you immediately see the die that you use in a game. So like a dice that you're like the game die versus, this is the German section of die, which these are sentences from Wikipedia. So apparently there's enough random German sentences in there, and BERT definitely thinks that is grammatically different. And maybe this whole thing is German die, as well as I'm going to actually color this not by part of speech for clarity. To die in the normal death sense, and we see that even within that, there's dying out or dying, like non-humans things dying, right? Like a cell may die, and that apparently BERT understands that is fundamentally different than, Louisa's friend dying, somebody else, like a human dying. So humans dying, inhuman things dying, and then some maybe sentences that are all similar in other ways. And then The last one I wanted to talk about is hot. I think this one's really interesting because it is truly the same word in all of these sentences. Well, okay, that's a bit of an exaggeration, but for the most part, a lot of these are talking about temperature. And you still get these really, really strong clusters. Hot is used often as a bigram. So you have hot air balloon versus hot temperature relating to the climate and summer and seasons and that sort of thing. Yeah, I'm not sure what these ones are. Hot seat. Yeah, hot topic, hot seat, hot discussion. So hot in that it's like exciting and intense. So I guess, yeah. And then the other thing that we can do with this visualization is see how these clusters develop through the layers. So we're looking at the last layer right now. But if we look at internal layers, we can see, hot air is always a very cohesive cluster, but for example, I don't know, other of these clusters are slowly building their way up. And at the very early layers, this is one layer of contextualization. So one path through a transformer block. There is almost no clustering at all, other than some bigram sort of stuff. And something that we found in the word sense tasks, as well as there's another paper that came out about BERT rediscovering the NLP pipeline, is that there are some probing tasks that are more successful at internal layers rather than at the last layer. And so this is kind of, by visualizing these layers, you can start to maybe see what BERT is learning at what stages and what it might be forgetting in the service of a later task. And something that I think is something I would love to tease apart further is what is the context of how much of this is vocab based. So how much of clearly hot air balloon is a phrase, and BERT immediately sends that to a different section. But the baseball section that we were seeing before, if there is a context of walk that didn't have to do with baseball but had a lot of baseball vocab, how would that affect it? I think that's an interesting direction for further research. So that's, and then here's a still from our paper with the same visualization annotated. So that is about it for our talk. As I said, we're looking to investigate where and in what ways BERT understands or does not understand both syntax and semantics through a series of visualizations and more analytical experiments. I guess if we have time for some questions from the audience or from Suhas, that'd be great.
Thanks for the demo, Emily. Okay, I want to go back to the question that Andre asked, and if I understand correctly, I think what he asked was what you already explained in the paper. It was basically about why the parse tree distance seems to correspond to the square of the Euclidean distance. And I think you have a proof for that, and you explained it, mathematically. Can you give a brief intuition about that?
Is the question like, why does it not correspond to L1 distance? Yeah, I think the intuition there is just that if it were L1 distance, then for a tree, imagine like for a tree with two nodes, it would be collinear. Like the idea is that if it were L1, there wouldn't be a way to embed the tree such that you wouldn't have child nodes that were on top of each other.
Do you want to draw it, or would that be harder?
Actually, maybe there's. Does that make sense? Does that explanation make sense?
Yes, it definitely does. Andre, is your question answered? Yeah. So are there any other questions from the audience? There's a question from the audience. What do you think about visually grounded language learning as a potential avenue for future improvement?
I think it's fascinating. I think that there's, I don't know a ton about this field, so from far away, I'm very interested in it, but I think that some of the questions we were trying to understand are like, what does it mean to understand language, and to what does it mean to actually have language describe the world itself? And we can kind of get at that through all of these, BERT clearly has some understanding of a mental model for the world, or no. We were wondering whether BERT has an understanding of a mental model for the world. And I think it's really hard to develop that mental model if you're only ever looking at text data. And I think that an image-based, if you start being able to refer to actual objects with language, that's much more similar to the way that humans learn language and learn communication. And really all animals understand communication as very visually grounded. And so I think if there were a way to do that at scale in a machine learning context, I'd be fascinated by that.
I think the big fundamental question that drove this, and I think drives all of the sort of Bertology research, was, just standing in awe and seeing how incredibly good these language models were at doing what we thought up to that point was purely only human doable language things. And the natural question is, when you see a model that's so successful at doing these human language tasks, is it learning human language? Is it learning language in the way that we understand language? And obviously there's a lot of debate and sort of complicatedness around what language is and how it's represented in our minds. But I think intuitively as a person, you kind of have a sense that, there is some hierarchical structure, there's sort of a tree-ness to it, and there's subtle context for words. I think the really interesting thing that we sort of have seen, and I think other papers and other authors are coming to a consensus, is that BERT is certainly picking up some things that look a whole lot like those things, right? It's representing information that is analogous to some of these theoretical language primitives, but it's not really the same thing, right? And I think it really has a lot to do with the fact that this is just statistics on massive corpora of text, and there's no, BERT's never seen an apple before. It doesn't have any notion of physics or the world of, it doesn't know what a color is, aside from the fact that it lives with other words that have to do with how it's being used. So it's neat. You see the shadow of all this stuff, but maybe maybe training these networks in a vastly different context or paradigm, maybe then you'll be able to see some new really cool emergent properties start to come out.
Okay, so there's a question on YouTube. Is there a way to quantify the quality of the generated embedding space, like from sentence structure to semantic capturing perspectives? If so, can it be used as a pointer for downstream tasks?
That's a cool question.
Yeah, I feel like that's the big question, right? Is that we have all of these giant embedding models that produce some sort of embeddings, and so that's why Blue Score maybe is a way of evaluating those embeddings, or you have all of these sort of proxy tasks but I don't think there's any one way, right? There's sort of accepted ways from the field, but
yeah, one thing that we've been talking a lot about recently is trying to assess the embedding space, quantitatively. How evenly distributed are embeddings in the embedding space, and is there some notion of the embedding quality, right, that we can measure in a way that isn't just us hand waving and sort of saying. There was which paper was it? There was just something a couple days ago. Do you remember what it was called? The one that Martin sent.
Yeah, there was a paper that looked at how claims about self-similarity between embeddings should be relativized to the overall embedding space. I forget what the paper was called though, but it was something about the anisotropy of contextual embeddings, how they actually occupy this sliver of the space as opposed to being more evenly distributed, as you might assume.
Thanks. So there have been a few questions on LinkedIn too. So let us go. Will you be posting the experiments? Okay, actually, there are two blog posts and I actually posted a link on the link to those blog posts on the chat, and there is also the link to the context atlas, which I also posted on the chat, and I think I will add it to the description section of the YouTube channel. But are there any other links that you have where you have posted your findings?
We published our experiments as part of our NeurIPS submission. I think NeurIPS makes that public, right?
Yeah, we can follow up with a link to that.
Yeah.
Another question from LinkedIn. So, BERT contextual embeddings apparently works better on English language only. Will it put same word translation in same cluster as well or not?
That's a great question. We haven't tried that experiment. Another member of our team a couple years ago, this is not BERT related, but NMT, the neural machine translation model, definitely does, but we haven't tried similar experiments on BERT. That's a great, it's a great follow-up, we should.
Okay. Amir has a question. Isn't what you are describing right now essentially, in a way, a knowledge graph, in the sense that you are mapping out the semantic and syntactic relationships between tokens?
So, sorry, can you repeat the beginning of that question? Or unless you had a...
Is the question, is it sort of a knowledge graph, or is the...
Yeah, in the sense that you are mapping out semantic and syntactic relationship between tokens. So can you say that it's essentially kind of mapping out a knowledge graph?
I think it's a really subtle, I mean, this is, take this with a grain of salt. This is my take on this. I think this is fascinating. But it's interesting. For any given word being used in a given sense, right? Like hot dog versus hot air balloon, right? Those two hot embeddings are nearer to each other, right? Like all of the hot dog hots are near each other. All the hot air hots are near each other, but they're all different. They're all subtly different, right? Like every single embedding is a little bit different. And there's an argument to be made about language that suggests that that is in fact the way that it is. Like every use of a word is a little bit different. But there's another way of looking at it, which is like the hot in hot dog and the hot in hot air are their own little platonic hots of a given sense, right? And like those are the same, they're immutable, they're like perfect hot of their given sense. Or like walk as a noun, walk as a verb, walk as a baseball thing, or like. And I think in the traditional like knowledge graph based, constructions, people have made these big wild data sets of, walk as a baseball term, walk as a noun, walk as a verb. And they're like very specific dictionary embedding or dictionary definitions that like have a node to another type of concept or something. But in BERT, it's all very messy, right? It's like those embeddings are kind of like near each other. And to what degree they're near each other and to what degree that's expected based on their sort of overall embedding space, like we don't actually like really have a good way to quantify that or understand that even. But it seems apparent from our experiments that like it's fuzzy, it's messy, it's like the result of just contextual information being injected in. So in my mind, like the way that I always think about it is like this is a shadow of maybe a knowledge graph. Like, and there's some really philosophical questions that this like gets into if you take it too deep, because it's like, what is the nature of this information in the perfect sense? And I think it's really a tricky question to answer in a really satisfying way. But I do find generally like, I like to think of it as a reflection of some higher reality that's being captured in the statistics of the embedding space. and it's like potentially very edifying to like look at what that information is in BERT. But like, I don't think BERT has a knowledge graph baked in implicitly. Like I think it's a little more subtle and a little more noisy than that.
Thanks. So there's a question from Billy. Can you speculate on incorporating the probing into a transformer model so that the model outputs a tree?
The model outputs a tree?
So wait, sorry, what was the very end of that question? So that the model outputs a tree?
Yeah.
Oh.
Can you speculate on incorporating the probing into a transformer model so that the model outputs a tree?
Yeah. Is that like you mean like a transfer learning task on top of BERT, or as part of the training of BERT itself? I feel like as a transfer learning task, like totally.
Yeah.
As in internals of BERT, you could.
Mm-hmm.
Yeah.
I mean, arguably that's potentially already happening. There's like these, I think there's like a fully connected node at the end of each of the encoders, and maybe one of them is doing this job of preserving the syntax tree.
Yeah. Doing it explicitly would be interesting. I don't know if it would help. I don't know if it would.
Yeah, it is interesting now. Like somehow that information is being encoded and passed around, right?
Mm-hmm.
It's like, you wonder if it's like, if you could improve it by making that very explicit.
Yeah.
I don't know.
Yeah.
It's really interesting.
Someone should try it.
Yeah. And another thing that is just nice to remember is that these trees are made up, like dependency grammars. They're not like some naturally occurring thing that we want BERT to grab onto. They're this thing that we invented that we're checking to see if BERT has found as well.
That's a really, really good point. Yeah. I think, I alluded to this in one of the early slides about the tree distances, like one of these, where certain things were further or closer than we would expect. But I think it's really important to sort of like reiterate the point that Anne just made, which is like these trees are essentially made up. They're kind of real in the sense that there is definitely some agreed upon hierarchical structure to language that most linguists kind of like sort of agree is real. But the trees are sort of a device. Like the first trees are a tool that linguists have developed to sort of give some structure to somewhat unstructured data. And there's a lot of sort of, it's not controversial, but there's debate and sort of like,
like
understanding that they're not a perfect representation in the linguistic community.
Like maybe BERT just came up with a slightly better one, and that we shouldn't mess with it. Or maybe it would help us to help it to give us starting place of at least what we think is the case.
Right.
That we're reflective of the way that humans actually speak.
Right.
So we have another food for thought question. Can your approach help with model compression? If you understand how BERT is understanding language, can you use that knowledge to trim it to be lighter?
Yeah. You can try to make a smaller language model and see whether it still exhibits these properties of language, but that's not the question.
I mean, these probes can serve as like dimensionality reducers for the output embeddings. So not distilling the model itself, but if you just want smaller embeddings that still capture the information, the linguistic information, then you can use one of these probes.
So the paper that Anne, you mentioned, but I can't remember what the title was. They were looking sort of at embedding space and the distribution of words in the embedding space and whether or not you should expect them to be closely aligned. And I think one of the takeaways, yeah, we should just find this paper. But one of the takeaways was that BERT was like, they argue that BERT is just massively over parameterized.
How contextual are contextualized versions?
Yeah, sorry, this was just like yesterday, so I couldn't remember what to do.
This is great further reading for anyone who's interested in BERT interpretability.
Yeah, it's really, really cool.
Yeah, actually, we invited this particular author,
Oh, cool.
uh, but he couldn't make it. But he promised a blog post, and yeah, it was there. So yeah, I'll be sharing this with the community. So
Yeah, it's a great blog post.
it's a great blog post. Yeah. So if we do not have any more questions, I think we'll be wrapping up. And I would like to thank Emily and Andy for a wonderful, engaging presentation. I think everyone is very excited to see this work, and we had a lot of interesting questions. Thanks to the audience for asking them, both on our YouTube and our LinkedIn channels. And yeah, again, I'd like to thank the authors for this engaging presentation, and just like to say that next week, since we had folks from Google on, we are legally required to bring folks from Facebook next. I'm just kidding, but we are actually hiring researchers from Facebook Research Paris in our next spotlight session on February 18. And they will be talking about their recent paper that has made a lot of waves in the ML community, which is called Deep Learning for Symbolic Mathematics. Please join in, and bye for now. Have a nice afternoon.
Thank you.
Fine. Yeah, thanks
Thank
for
you,
having
thanks
us.
for having us.